day 36 of 50 days of tutelage, and in today's class, I'll be talking about chemical equilibrium. So before we go into chemical equilibrium, I will need to talk about the type of reaction where chemical equilibrium can actually take place, and that is a reversible reaction. So a reversible reaction is such reaction that can take place both forward and can also take place backward. So from what we have learned in the previous class, we already established that when reactions are taking place, it happens that some reactant, so some substance known as reactant, will react together and they will give birth to a product. So reactant, they form product. So we understand that reactants are being used up and products are being formed. That was what I explained in the last class. But if the reaction is a reversible one, so in this case, we have something of this nature, and we have something of this nature. So this symbol represents a reversible reaction. This actually implies that as the reactants, as they are turning to the product, they are also turning to the reactant as well. A very good example is when you put a certain amount of water in a boiler and you supply it to that boiler. What happens is that the forward reaction is going to be such that this liquid, that is the water, is turning to vapor. But over time, when you check the lid, if this boiler has a lid, when you check the lid, you notice that some of the gases, some of the vapor that are escaping to the lid are also turning back to liquid. So meaning that liquid to vapor, vapor to liquid. That is exactly what a reversible reaction is about. So for reactions that are reversible, when do we now say chemical equilibrium is attained? This thing happens, it goes on and on. Reactants are turning to products, reactants are turning to products. Maybe few of the products are turning back to reactants. But it gets to a point whereby reactants, they have done so much such that products are turning also to reactants, and product is now beginning to come up with the reactant as well. And the rate at which the reactants are being converted to the product is now the same thing as the rate at which products are being converted to the reactant. Now take note, I emphasized on the rate at which the conversion is taking place. I'm not talking about the amount of reactant that is being converted to the product or the amount of product that is being converted to the reactant. I'm talking about the rate at which they are being converted. Once these rates are the same, then you say equilibrium has been attained. So it does not necessarily mean that you have the same number of reactants or the same number of products. What is happening is the rate at which they are being converted to each other. So which means that this is the kind of reaction whereby you can either approach it from left to right or from right to left. It doesn't really matter. It can happen from left to right and from right to left. And that is the basic introduction to the concept of equilibrium. So equilibrium is a type of reaction whereby there is a reversible reaction, that's number one, and this reversible reaction is occurring such that the rate of forward reaction, that is reactant turning to product, is the same as the rate of backward reaction, that is product turning to reactant. Now there are some characteristics that we notice in chemical equilibrium. Whenever there is chemical equilibrium, that is a reaction has attained that level, there are some things that we notice. We notice that if the system is not a closed system, that is an isolated system, if the system can interact with the immediate environment, then equilibrium will not be reached. For instance, this situation I described earlier of boiling water, if the vapor can actually escape, then equilibrium will not be reached because the vapor that are supposed to condense to form water back, they will be escaping to the atmosphere. So you need a closed system for equilibrium to occur. That's number one. And also, like I've explained, it is what? It is dynamic. Both forward and backward, they are what? They are the same. Forward rate and backward rate, they are going to be the same. So another thing again is that the concentration of the reactant and product, they remain constant. The concentration of the reactant and product remain what? So if a system has reached equilibrium, so if this is at a certain level of concentration and this is at a certain level of concentration, then this concentration will never change. So if this concentration is A and this is B, you cannot have A plus 1 or A minus 1. You cannot have B minus 1 or B plus 1. It remains like that. Now, does it mean that A is equal to B? No. It does not necessarily mean that A is the same thing as B. It just means that the value of A and the value of B. So these two values simultaneously, they remain constant. And also, last thing here is that introduction of catalyst does not actually affect the position of equilibrium. It does not affect, so it doesn't make the equilibrium to go to the left or to go to the right. It keeps it at equilibrium. The only thing it does is that it can help us attain equilibrium faster. So this system now, before it attain equilibrium, if you introduce a catalyst can actually help it attain equilibrium faster. That is a positive catalyst in this sense, making it uh, reach, increasing the rate of the reaction. So that's basically what a catalyst will do in that situation. Now, let us proceed to a principle that actually guides us when it comes to dealing with anything under equilibrium reactions. And that principle is called the Le Chatelier's principle. Le Chatelier's principle. I struggle with spelling these names, so I'm just going to try. In case I do not get it correctly, you just have to like check it out. So Le Chatelier's principle. So quickly, before I give all the principle, what is this principle all about? The principle is all about the fact that if a system is already in equilibrium and you forcefully you decide to cause a change, an imbalance in the system is going to adjust itself and return back to equilibrium. That's basically what it's talking about. So if a system is already in equilibrium, so let's say this is the system finds itself in equilibrium already, and you decide to introduce something there to cause an imbalance. So let's say this is the system now in equilibrium. So what it's saying is that if you decide to bring something here now to cause imbalance, this guy will tilt towards this place. Now I'm just using this one as an example. This is not the uh, the chemistry aspect. This is like physics, but just for you to know. So introducing this mass now will cause this guy to tilt this way. So what's going to happen is that this guy is going to balance itself. What it does is that it shifts the equilibrium position. It favors a particular reaction. So as you can see now, the right now has an extended length, and then the left now has a reduced length. So this is exactly what Le Chatelier's principle is talking about. Le Chatelier's principle just says that when you introduce a new thing, a distortion, a perturbation into an already balanced or a system that is already in equilibrium, the system is going to adjust itself and it's going to go back to the state of equilibrium. So these are the things that affect. Number one is change in concentration. So if you change the concentration of a particular point in the system, change in concentration. For instance, you can change the concentration. So we're going to be dealing with reactant versus product. If you change the concentration of the reactant, it will affect this whole thing if it was already in equilibrium. For instance, if you lower, that is, you reduce the concentration of reactant, what is going to happen is that this one is going to now have more concentration. For instance, if their concentration in equilibrium, if it was 4 versus 6, and you now decide to say you want to actually decrease the concentration of this one to 2. So what is going to happen is that some of these will actually readjust itself. Like I told you, reactant is forming product is forming reactant. If their equilibrium number is 4 versus 6, that is, this 4 versus 6 keeps them in equilibrium. Then you now decide to reduce this one, you reduce it to 2. So what's going to happen is that if you try to match this, like let's say 4 to 6, what exactly does it really imply? So 4 to 6 mean that, so if I have 1, 2, 3, 4, and I have 1, 2, 3, 4, 5, 6. So let's see how this actually balances together. So what this balance together is that you see that we can have this group here and we can have this group here. So for every 2, there's going to be a 3. So you now want to do this thing, you want to reduce this. You want to reduce this, and this is going to be out of the entire thing. Now this is what you now have now. This system is no longer in equilibrium. So what is going to happen is that this system is going to make itself is going to readjust and try to make this guy form. So instead of it being a product now, it's going to go on undergo some kind of reaction and it will form a product back. So in that situation, before you can have equilibrium now, by the way, I'm not using a perfect number. I'm just using, I'm just trying to do one or two things. So in this case, we've noticed that every three forms two. So that means that this guy will want to go back to equilibrium. And if this is two now, there will be more reactants that will be formed in that situation. So the product now has excess. So that's what I just showed you now. The product now is in excess. So the product now needs to react and form some of the reactants. That's the way it works. So if you reduce a part, that part that you reduce will be favored. So meaning that more reactants will be formed, therefore backward reaction is favored. So reducing a portion, reducing a part of the reaction will always result in the fact that equilibrium will be shifted to that part. So automatically, when you increase a particular part, that implies that equilibrium will favor the other part. So let me go over that again. If you reduce a particular part, equilibrium will shift to favor that part. But if you increase the concentration, equilibrium will shift to favor the other part. So that's exactly what this whole thing is all about. That is how concentration, altering the concentration, that is how it affects equilibrium. So let's now take a proper look at it now. So if you have the reactant versus the product. So let's say in this place you have like A1 plus A2 plus A3 to give B1 plus B2. So these two are the product and these three are the reactants. So let's say in this situation now, I remove A or I reduce A. So what is going to happen is that equilibrium is going to shift and more A will be formed. So therefore, equilibrium is shifting to the left. Reduction in a particular element from the left. When I say element, I'm not talking about the element in chemistry. I'm talking about like a substance. When a substance is reduced on the reactant side, that is, you reduce the concentration, then equilibrium is going to shift to favor the reactant side, meaning it favors the backward reaction. So more of the reactants will be formed to adjust back to the equilibrium position. But if you do the converse, that is, you increase the concentration of A, increasing the concentration of A means that more product has to be formed. Therefore, forward reaction is favored. And if you go about from the product side and you do the same process as well, it's going to happen the same way as well. Reduce B, then more product will be formed. Forward reaction is favored. Increase B, then backward reaction will be favored. More A is going to be formed in that process. And that's the effect of concentration. The second one is effect of temperature. Now for this one, temperature, we can only discuss it based on endo or exothermic reaction. I've already explained the difference between endothermic reaction and exothermic reaction earlier. So what happens is that whenever you increase the temperature of a system, endothermic reaction will be favored. So whatever side is the exothermic reaction is going to be not favored if you raise the temperature. So what I'm saying is that if you have a reaction A to B, and then the delta H of this is positive. From there now, you know that this is an endothermic reaction. I explained that to you earlier. So if this is an endothermic reaction and you increase the temperature in this system, what's going to happen is that more B will be formed because this is an endothermic reaction. By the way, the reverse process, if this was the whole thing in the first place, if a reaction is endothermic, when you reverse it, it's actually going to be exothermic. So that means that if you increase the temperature in this place now, it doesn't favor exothermic. So instead of it to favor the forward, it's going to favor the backward. You can see that it still leads to the same thing. In this place, this is endothermic. So because it is endothermic, increase in temperature favors forward reaction. This one is exothermic. Increase in temperature does not favor exothermic reaction. Instead, it will favor the reverse process. So therefore, if this is exothermic, that means that backward reaction will be favored. That means that more B has to be formed. So you can see that even though I reverse the two, increasing the temperature still close and then remains on what? Forming more B. But for exothermic reaction, what will favor them is decrease in temperature. So if you decrease temperature in this case now, what will favor is that more A will be formed, backward reaction. And if you decrease the temperature A, because it's already exothermic, it will favor it. So decrease in temperature favors exothermic, while increase in temperature favors endothermic. And the reverse of endothermic is actually exothermic. Now, the last one is the effect of pressure. Now, this pressure only affects gaseous products and reactants. That implies that if you do not have, maybe let's say in this place now you have A is a gas, plus B is a solid, and then you have this, you have C is a liquid, plus D is a gas. Now in this case, let's say we have these guys are in the mole 2, 4, and you have 1, and you don't need to put 1. So let's say you have them in this particular amount of moles. So what you notice here is that, let's say this is 3 actually. Now, if you want to determine the effect of increase in pressure in this place, note that increase in pressure always favor the side with lesser number of mole of gas. Increase in pressure always what? Favor the side with lesser number of mole of gas. So in this case, if you want to do the general number of moles, you will think that this is 2, this is 4. So total number of mole here is 6. This is 1, this is 3. Total number of mole is 4. So if you want to go by that just number of mole, that means that increase in pressure will favor the forward reaction. That is, more of this guy will be formed. However, there is a clause there. It has to do with gases only. So what is the number of mole of gas here? 2. And what is the number of mole of gas here? 3. That implies that the left-hand side is the one that has the lesser number of mole of gas. So therefore, increase in pressure will favor the formation of more of the reactant side. Hence, backward reaction is favored. But decrease in pressure will do the otherwise. So decrease in pressure will always favor the side with higher number of gases. So if they both have equal number of gases, then pressure will have no effect in that system. If they have equal number of gases from the reactant and the product side, then that means that pressure will have no effect on that system. So that is basically how effect of pressure works. And so lastly, before I finish the class today, I will be talking about the equilibrium constant. So the equilibrium constant, if you have a certain reaction and you have this plus where these small letters represent their number of moles in the reaction. So if you have something of this nature, let me write that very well. And you have this showing that it is a reversible reaction. And you have C plus D. So the equilibrium constant Kc is given as the concentration of of the product raised to C multiplied by that of D raised to D divided by that of A raised to power A, then over that of B raised to power B. Now, one thing you need to take note is that this equilibrium constant, and we are doing it in terms of concentration, that is why we are putting C here, in terms of concentration, it does not affect when you have liquid reactant or product, and it also does not affect solid reactant or product. So when you have pure liquid or pure solid, it does not what? It does not affect them. So when we're dealing with situations like this, what we are actually really concerned about, we are concerned about those that are in solution. So we are talking about aqueous solutions. That's what we're dealing with. So because when we're talking about concentration, you have a solute inside a solvent. But the moment you're talking about a pure liquid, it is not, nothing is being dissolved inside. or you're talking about a pure solid, it is not dissolving inside something, then those guys, we don't include them in this entire thing. So therefore, most of the time, we're going to be dealing with aqueous solution. And if it is gases that are involved, we deal with Kp, equilibrium constant in terms of pressure. And we just apply it the same way as well. So take note, if any of these is actually a pure liquid or a pure solid, then you do not have to include them in this expression. For instance, if D was a liquid now, then I will rule it out from the entire expression. And so what do we know about this equilibrium constant? Is that if Kc is greater than 1, if Kc is greater than 1, it means that the more product will be formed. So product will be favored in this case. And if Kc is less than 1, it means that reactant will be favored. So this one, Kc greater than 1 means forward reaction is going to be favored. Kc less than 1 means that the backward reaction is going to be favored. And if Kc is equal to 1, in fact, Kc being equal to 1 is what denotes equilibrium itself. And so that's basically what this is all about. And that's the summary on chemical equilibrium. That's everything you need to know. I've explained the Chatelier's principle, and I've also explained what it means for a system to be in equilibrium. So that's it for today. Make sure you like and subscribe to the channel if you have learned something from the video. I'll see you in the next one.